All right, last part of 1.3 is something, it's called the Squeeze Theorem. I think there's other names to it, also called the Sandwich Theorem, the Pinching Theorem. But let's go over this. So the next theorem concerns the limit of a function that is squeezed between two other functions, each of which has the same limit as the given x value. So if we were to graph our 3, so we're approaching c in all cases. We've got our f of x in the middle here. Let's say that's that function. And we've got this value. G of x, say, is up here. And h of x, say, is right here. Okay, and if you notice, as they're approaching c, every single one of those functions is approaching the same value. But in terms of the same y value, that is. But in terms of the picture, obviously they're different. So h of x is less than or equal to f of x, which is less than or equal to g of x. And again, I'm basing that predominantly on location. G of x is above f of x, which is above h of x. So what the Squeeze Theorem says, it says if we have that compound inequality, so if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x values, so for all x in an open interval, okay, so that would be one that has in parentheses, not brackets. So if in an open interval that contains c, so c is the x value that we are working with, containing c. And we're going to just say, we're going to add this in, except possibly at c itself. So it does not necessarily have to include c, except possibly at c, because keep in mind, limit is what it approaches, not what it equals. So it could be, there could be an open circle there. And if we know that the limit as x approaches c of h of x, so our lower function equals capital L, which is just limit, and the limit as x approaches c of g of x is also equal to uppercase L. Okay, so the lower function has a limit equal to L, and the upper function has a limit that's equal to L. What the Squeeze Theorem, Sandwich Theorem, Pinching Theorem, whatever you want to call it, says is that if the lower limit or the lower function has a limit equal to L, the upper function has a limit equal to L, if they are all coming together at that same particular c value, then that means the middle function also must as well. So the limit as x approaches c of f of x, so that's your middle function, it not only exists, so exists, and is equal to L. Is equal to L. Okay, and this is not used often. You might see it, if you ever see a compound inequality on one of the homework problems that I give you near the end of the section numbers, that's probably where you're going to be using this. All right, now two special trig limits that you need to know. So just like in pre-calc you had identities, now we got some trig limits. So the limit as x approaches 0 of the sine of x over x is equal to 1. And the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. Those are two that you're going to see me use in the next few examples here. All right, so we have two examples we have to go over. So we have the limit as x approaches 0 of tan x over x. So what we're going to do is we're going to break it down. So we have the limit, because you can't sub-zero in, you get a 0 in the denominator. So we know that the tangent of x is sine over cosine. So I'm going to rewrite my numerator. Step 2, I'm now going to bring that denominator down because I can't have fractions left over in fractions. So I have to simplify. So I have x cosine x. Now what I'm going to do is I'm going to start to break it apart. So we want to now focus on these functions up here. Not saying you're going to use them all, but if I now break apart this fraction here, I can split it up into two things. So one of them is going to be made up of the identity sine x over x. And the other one is if I take a sine x over x out, I'm left with 1 over cosine x left over. All right, so one of the properties we went over on the first day of 1.3, it was in the middle of the note sheet, said that if you're taking the limit of a product, then you're going to take the limit of each one separate, and then you're going to multiply the limits together. So this one right here is an identity. That one's fine. Okay, so that's equal to 1. That's right above. Second one, though, this is where we got to use direct substitution. So direct substitution. So we get 1 over the cosine of 0. At 0, we have the point of 1, 0. So the cosine of 0 is 1. So this gives me 1 times 1 over 1, which is going to give me a limit that's equal to 1. All right, second and final example in these notes. We have the sine of 4x over x. So it looks similar to the identity, but just keep in mind there is that extra 4 in there. So that definitely plays a part in this type of problem. So you can't have the extra 4 in there if it's not in the bottom when you're using the identity. So we have the limit as x goes to 0 of the sine of 4x over x. The problem is I don't have a 4x in the bottom, but I certainly can add that in, okay? You can add a number in the bottom, but if you add it to the bottom, you also have to add it to the top. It cannot go in the actual sine function itself, so it has to stay on the outside. So what I would then do is, this here is the identity from the other page. So the other side of your note sheet, this was what the identity said. And you can modify that, but keep in mind, oops, sorry. These two things need to be exactly the same for the identity to work. So at that point, we do have those. They're both 4x, but this extra 4 has to get kicked out. So it's going to be 4 times the limit as x goes to 0. And we have the sine of 4x over 4x. Now this is the identity, which is equal to 1. So we get 4 times 1, which is equal to 4 for that one. Now I just want to show you how it could be slightly tweaked. So there is an alternate way of how that looks. You could also see it, same type of problem, but you might see it looking like this. And there are definitely a difference in how you have to approach this. So instead of the 4x being in the top, it's in the bottom. So if it's in the sine function, that's where, if it's in the sine function, that same value has to be in the bottom. But if you look at this one, only x is in the sine function. So the only thing I care about is the x that's in the bottom right here. The 4 can actually be pulled right out. But what you have to be careful of, the 4 is in the denominator. So it's actually a 1/4 times the limit as x goes to 0 of the sine of x over x. This is now your identity. And you end up with 1/4 times 1, which is equal to 1/4. So add that example in there just because there is a difference between how we did the top one and how we did the bottom one in terms of your approach. If the extra piece is in the sine function, you have to add it to the denominator and to the numerator. But if the extra piece is in the denominator, there's nothing else to add. You just have to pull that value out. But just be careful because it's in the bottom, so it has to stay in the denominator.